So let's just take a quick visualization of the different polarizations as another quick way to get familiar. But as you can see, linear polarization, if you have the two components in sync, if you decompose it into x and y components, then that just means it's still linearly circular. It's linearly polarized, but it's now off axis in terms of the xy plane. So you still have the linearly polarized wave, but in this view, it's just rotated. So it's not completely just in the case of x, as we described before. And then similarly, the magnetic field, which we didn't show, is just in 90 degrees to it, so that when you take the cross product, it's still propagating in the z direction. Now, in the case of elliptical polarization, what you see is that because of the phase that x and y have, if you're just sitting at z equals 0 and looking at how the fields change, what you end up seeing is that the electric field doesn't increase or decrease. It stays at a particular magnitude and it just rotates. And in this case, with the way this is set up, you see that the y component, if you have the y component lagging the x component, the thing will rotate in a direction such that if you have your thumb pointed in the z direction, your right hand curls in the direction of this rotation here, and so it's right hand circularly polarized. And the last situation is that if the criteria of the x and y component being the same is broken, or if the phase between the two is not a multiple of pi half or pi, then you end up having it be elliptical polarized, in which case the only other thing that you need to identify is just whether it's right or left hand elliptically polarized. And again, the main way to do that is to get this between minus pi and pi, look and see whether EY leads or lags EX, and then use that to determine which hand it is. The other way is if you like to work through the math, just set z equal to 0 and plot that parametric equation and just see if the thing rotates in the clockwise or counterclockwise direction. So let's conclude that with just a roadmap for how to diagnose polarization. The first step is to get it in phasor form and get it to look something, in the case of z propagation, something where you have some x component plus some y component with a phase difference with, let's just say it's in a lossy medium and it's propagating in the plus z direction. Get it into this form. And namely, also make sure that that you make the adjustments so that this is between minus pi and pi. And so after that, you just make a series of determinations. So first of all, is the x and y component in phase, meaning that phi is equal to some multiple of pi. So this is either, this could be plus or minus, but the point is that e to the j phi ends up being equal to plus or minus 1. So if the answer is yes, then it's linearly polarized. And you can write it in EXX is going to be, you're going to be able to write it something like that. However, if it's not, then you need to figure out whether it's elliptically or circular polarized and what the handedness is. So first of all, to be circularly polarized, it needs to meet two criteria. So the x and y component need to be equal in magnitude, and so both of these need to be met. Phi is going to be equal to some multiple of pi half, right? So if I were to just be very general, I would say it's 2n plus 1 over 2 pi. But if you reduce this so that it's between minus pi and pi, this should just be equal to plus pi or minus pi, right? And but I'll write it this way so that it's more general. But if both of these are met, then it's circularly polarized. And then you just have to determine the handedness, right? So if phi is equal to plus pi half, then in the case of positive z propagating, it's going to be left-hand circularly polarized for plus z propagating. So remember, if it's negative z, you have to flip these results. So you would say right hand instead of left hand. And then if phi is equal to minus pi half, then it's going to be right hand circularly polarized. If the answer is no, then it's elliptically polarized. And then you also have to determine handedness, right? So if phi is greater than 0, then it's left-hand circularly polarized. If phi is less than 0, then it's elliptically polarized, right-hand elliptically polarized. And again, this is for plus z propagation. So if it's minus z, then you have to reverse your results accordingly. And then separately, this is z with the phasor rotating in x and y. You can also easily, swap these letters so that it's propagating in a different direction. So those variations go without saying. And so let me end by just talking about applications for polarizations. So one thing that is important to note is that this is a really key feature of antenna design and the wave that you choose and the kind of polarization that the antenna is designed to receive, right? So, and if it turns out that there's a mismatch, then you end up with getting polarization losses. So, for example, if you have a linear antenna, so it captures things that are polarized in the x direction. So let's just say you have a linear x linearly polarized antenna. Then what happens if you end up getting a polarization mismatch, right? So if you end up receiving a wave that's in the x direction, then you have 0% loss, right? But if you're in the y direction, then what do you end up getting? You end up getting 100% loss, right? Because it's completely perpendicular, none of the current gets captured. But what about a circularly polarized wave? So one of the things is if it's circularly polarized, that means that there's an x component and a y component, and they're equal in size. So if you only capture the x component, then you get 50% loss, right? And then the other example that I have for applications is a polarizer filter that you often use in photography. So one of the key features of reflected light on water is that the water will reflect a linearly polarized light off of it. And so if you have a polarizing filter on your camera and you can rotate it, depending on whether you rotate it so that it filters all of the light of that reflected polarization or none of the light, you can make your water look transparent or make the water completely reflective. So those are two applications where polarization comes in. So in summary, we looked at polarization, which is one of the aspects where this 3D propagating wave does not directly map to transmission lines. But in case of plane waves, we have the plane wave solution, but they can still be polarized in a number of different ways. And we determine that polarization by seeing what it looks like when you project it onto, if it's propagating in, say, the z-axis, what happens when you project the wave to the x and y-axis. And we have a map here to describe how to determine whether it's linearly polarized or circularly polarized or elliptically polarized. And separately, for the case of circular and elliptical, you also look at the lead-lag relationship between the x and y component to figure out whether it's right-hand or left-hand circularly polarized. And so in a way, this is the shape of the electromagnetic wave, and it becomes how well your system matches to that particular polarization has direct impact to how well your system performs, and it's another key knob that you use to engineer your electromagnetic wave as in your system.